I think these are what you asked me to do: a commutator and review the hydrogen atom solution. I went back and listened, and I wasn't sure what was said. Okay, good. So number one, cross product. We only really did one cross product. So this is it. So when you do a cross product, you always have a determinant, and the first row is always going to be the unit vectors. So I'm going to put E sub r, E sub theta, or excuse me, I'm going to do this in Cartesian coordinates. E sub x, E sub y, E sub z. Then so the first row is your unit vectors. The second row is the first vector here. What was that? Okay. Just want to make sure I didn't make a mistake, because you know that happens. The second vector goes in the second, or the first vector in your cross product goes in the second row, and then the final vector in your third row. And each one is doing the components of the column head. And then we just do that cross product, remembering our rules for the 3 by 3 or cross product determinant. So you always choose this row. And so you take the first element, E sub x, and then multiply by the determinant of its co-matrix, which is the matrix you get if you take out, the row and column you're in. And so I'm going to do that each time and then erase so I can continue on. So EX times that determinant, which is going to be YPZ minus ZPY. Now, it's important to note that you're going this direction with a plus sign and then this direction with the minus sign. If you arrows go from down to up instead of up to down, well, that's the commutator difference, right? So you have to make sure you're going in the proper direction. So there's my first one. So now I'm going to delete all of these inner markings. Maybe. And now I go to my second. Now, that whole Levi-Civita thing, you change the sign. You're alternating signs for each term. So the next one's minus E sub y. Then I cross out the row and column, and I take the determinant of my co-matrix, which is going to be xpz minus zpx. And erase those cross-out lines. Alternate signs, so I'm going to go back to positive E sub z, my unit vector in the z direction. And now why do I keep doing, well, you know what I'm doing, right? I'm hitting the top of the screen. That's why it's doing that. Crossing out the row and column for that one, I have determinant is xpy minus ypx. So now I have my 3 terms, one in the x direction, one in the y direction, one in the z direction. So just picking them off, since this one in red is the x direction, I have L subscript x equals ypz minus zpy. For the y direction, because of the minus sign, I'm going to reverse the order. So I'm going to have Ly is equal to zpx minus xpz. And then the z component so there is doing a cross product in something that's, well, the only one that's relevant for us this semester.
Can you go over why you switched the sign?
Sure, because I just had to distribute this minus sign. And so I put the minus sign here and minus, and that made a plus. And so that's all I was doing, was distributing it.
So would we need to change that to spherical coordinates? Because that's how we did it in class when we were finding angular momentum operators.
Actually, we didn't. The angular momentum, we did X, Y, and Z components. And then the Z component was the one that we dealt with specifically.
But we did.
Well, I'm obviously, I'm not looking at my notes. I know that all we actually worked with was these. I might have done them in spherical coordinates, but all we actually worked with was in Cartesian coordinates.
Because when we were doing the cross product, we did ER, E theta, E phi, and then we had R00 in the second column, and DDR 1 over.
Yes, that's right. We did.
Okay.
Now I remember doing that, but we never used that.
Right. So is it better if we were to do it on the test? It would be better.
Yeah, we'd just stick with Cartesian. Yeah.
Yeah, that makes more sense. Okay.
You're right. I did do that. Now to think about it.
Okay, scroll back up. How did you get that matrix from R across?
This matrix right here. So the first unit vectors is the top row, and then the first vector in the cross product in the second row, and then the second vector in the cross product in the third row. So these are just expanding. So our vector, and I've got to write down here because of space, our vector is equal to x in the e sub x direction plus y in the e sub y direction plus z in the e sub z direction. And so that's where the x, y, and z came from.
So if you knew that you had something that only had a component in the x direction, it would just be 0 and 0 for the y.
Right. Which is why when we did it in the polar coordinates, it was R00 for that row.
Okay. But there still might be momenta in those other dimensions.
Yeah.
Okay.
Any questions? Move on. Second problem, doing a commutator. So I just chose a kind of random commutator. Actually, thinking about it, may not have been the best choice, but I chose one. So if we're going to do this commutator, the way you do it is replace H with did I put three-dimensional? You don't have to. P squared over 2m, three-dimensionally, p squared is px squared plus py squared plus pz squared. Oh, let's at least put a potential energy with this. So there's our Hamiltonian, comma, px. And so if I can do it without putting the psi there, I will. If I have to take a derivative, I'm going to have to throw a psi at the end of everything. So in this case, I have that's still an x. I have those. Now the first one is the easiest one because that would be let's change it from a bracket to a parenthesis so it doesn't look like it's a commutator. That one's easy because that's just 0. The second one looks like it's going to be harder, but Py is a derivative with respect to y. Px is a derivative with respect to x.
I told your wife I'd give it to you.
Oh, okay.
Thanks.
Thank you. And so since this is only a function with y and this is only a function with x, those are going to commute. The x doesn't affect the y and vice versa. And I'm not going to show the third one because obviously z and x is going to be the same as y and x. So we have 0, 0, 0. And then I'm going to have VPX minus PXV. And so now I'm going to have to figure out what this is, which is going to be something a little more challenging. So I'm going to use my definition that PX is equal to H bar over I d dx and put a psi at the end. Now you have to remember I'm going to take out the psi when I'm done. I have to put here because I have something to take a derivative of to see what's going to do. So then I'm going to have v h bar over I d dx psi minus h bar over I d dx of v psi, which means I have to use the product rule in the second one. So I did the product rule for these two here. But we can see that these two add to 0. So what I'm left with is this. Notice the parenthesis here. I'm not taking the derivative of psi, just taking the derivative of v. And so that means I must have an equivalence that and remember, this last equality is because I had already determined that HPX was just equal to VPX. So we dealt with basically the two different ways we do it, either using already known commutators or having to put the psi in there and analyze it.
So that means that the momentum in a certain direction is only changing the potential energy of the system? Or how would you interpret that commutator?
Okay, so I interpret the commutator two ways, like we talked about in class yesterday. Number one, I would say that I cannot know the momentum in the x direction at the same time that I know the total energy because of the last part there. Or likewise, I can know the kinetic energy, but I can't know the potential energy at the same time that I know the momentum. So that's the first thing I would take from it. Then the second thing I would take from it is, if I have the potential energy acting on the momentum acting on a wave function that's minus, reverse the order, and then we have to add this in with it. So using that relationship. Because that's, I mean, when I was introduced to these, that's what I thought it was for. I thought it was simply so we could say, aha, if I have a VPX somewhere, I can replace that by PXV minus H bar over I dV dx. That was what I thought it was for when I first learned it, because that's mathematically what you're doing. But it turns out that it's much more meaningful to me now in terms of, why I said you can't know them both at the same time.
For the angular momentum operators, will we be given some of those, or do we need to memorize what each of those operators is?
Memorization is not a key. So like if, how to do something, yeah, you need to know how to do that. It's not like I can come with a blank slate and just know my math. But, if there's something like you're like, oh, I didn't think I had to memorize this, just ask me. Because usually, unless it's, I forgot what the meaning of momentum is,
Yeah, but like the ladder operators and that
Right. I would give you that.
Okay.
Any other questions about the commutator problem? Now, if the third one was a simple problem like this, we'd be done really early. Let me talk about the test before I go to the third one. I think there's 6 of the knowledge questions, and then I think it's 4 of the short problems. And so I don't remember what the other tests had, but I'm pretty certain they had generally more than 2 of the short problems. And yeah, I can't tell you what the problems are, I guess. That wouldn't right. I could. You're right. I could. Be able to do this problem.
Yeah. Those knowledge questions, like each worth 10 points or something?
No, they vary.
Okay.
What I will tell you, one of the knowledge questions is, there. Okay. One of the knowledge questions is this, right? You pretty much already knew that, right?
Yeah. Still not fun.
So,
the steps.
Yes.
Just like analytical solution.
And that's more than 10 points. So I went through and summarized in, kind of lengthy form, the actual process we did for solving the hydrogen atom. So we start with the time-dependent Schrodinger equation. And the first thing, which, I just said we do it all the time, we never come back to it, is you got to separate to the time-independent version, and that's the one we work with. You always have the time dependence, keep that as a separate thing. So that's what the first one is, just get the time-independent form, and then use spherical coordinates because you have a spherical symmetry in your potential energy function. If potential energy did not have the spherical symmetry, you wouldn't do it. Because let's be honest, it's generally going to be harder looking at, right? The math is not so fun. Then we have to do our separation of variables, and we have it in 2 steps. 2 steps? Yeah, 2 steps. So the first step is to define a function that has the radial part and the angular parts, because you have both psi both phi and theta. And when you put that into your Hamiltonian, then you can, by judiciously dividing everything by psi and then separating terms, you have terms that only have r as a variable and terms that have both theta and phi as a variable. So you take the terms that have r as a variable and you set them equal to the convenient constant of L times L plus 1. And at this point, you know exactly why we did that. When I went through it the first time, it was just, you'll find out that this was a convenient choice. You have to be honest. No one would ever come through the first time and say, oh, what should I make these equal to? I need a constant. L times L plus 1 sounds like it's probably a good constant. That wouldn't make sense. So it's a constant that's chosen because we know the end already. Then you take the angular part, which is also equal to L times L plus 1, and you say, well, I'm going to set my angular function equal to one function of theta and one function of phi. Do the same process, separate them, and you get two separate functions, which you set equal to the convenient constant of m. At least this time it made sense. You know, m, a, b, nobody cares what letter you use. So that one made sense. And then you get the azimuthal equation that turns out to be simple. You just have the second derivative with respect to psi is equal to, or second derivative with respect to phi is equal to phi times a constant. So that one is simple. You just have e to the, you have I in there because of the sign. So maybe it was a minus. I don't know. I'd have to look at it to see what the signs are. Yeah, it's equal to minus
One of the weird
m
things about
phi.
that, though, is that we ended up saying it was like equal to, we changed the e to the im phi into sines and cosines, but we didn't put any normalization constants out front. Why?
We didn't put normalization constants in until we were done.
Okay.
So in the end, we had actually, we didn't work out how the normalization constants are found because that's just another fun barrel of monkeys. But we had the normalization constant in our final equation.
Okay.
But yeah, you just wait until you get to the end because you're going to have a bunch of functions you have to put together. So the azimuthal function gave us, you had e to the plus or minus im phi. Is that right? E to the plus, yeah. And then we had to go to the theta version. And for that one, we had to use the Rodriguez formula to find the Legendre polynomial. And from the Legendre polynomial, we found the associated Legendre function. Yeah, exactly like Chad just indicated. I have never had to go through in my life, and would have had 4 quantum mechanics classes. I've never had to go through, and here's how you get, how you derive the Legendre polynomial or the Legendre function. Just it turns out that these are the solutions. Somebody did do all the work, and his last name was Legendre. After that, everybody's just said, look, he did it. Okay, so we have those, and then when we combine these, when we combine this with our Legendre polynomial, then we had our spherical harmonic. And the spherical harmonic has 2 indices. I think L goes down below and M goes up above because we had the 2 constants. And those 2 constants, each one gave us a quantum number. We had because of our boundary condition that it had to be repeating every 2 pi, we had the result that M had to be equal to an integer. And likewise, because of the polynomials and having the derivative, the Lth derivative, it turns out that L had to be an integer as well. And based on the Rodriguez form, based on Rodriguez and Legendre, we had minus M or minus L less than or equal to M less than or equal to plus L. So that came mathematically. Once we associate angular momentum with this, then I started talking about, total angular momentum has to be greater than or equal to the component in the z direction to get these limits. But it also came out mathematically before we ever even associated L with angular momentum or M with the orientation of the angular momentum. Just from these functions right here, it came out that you had to have this relationship.
Wait, so we knew the limits on L and M from another way than just the mathematical?
Well, we had, when we associated angular momentum with total angular momentum with L and the component of the angular momentum in the z direction with M, then we had a second way because the component in the z direction cannot exceed the total. And so that gave us a second way to enforce or to say that has to be true. The M has to be between minus L and plus L. So we had the raw mathematical, and then we had to understand angular momenta. They both agree, fortunately, that has to be the case. So with these spherical harmonics, and those spherical harmonics, that we actually normalized that separately. And so we got a crazy normalization constant for that. And then we went to the radial function. And when we were done with the radial function, we normalized that one separately. And then we put them together. So for the radial function, that one was actually hairier than the angular function because we first made a change of variable that just doesn't seem obvious. Making the change to a function u of r is equal to r times r of r. To me, it seems like, well, it's not buying me anything. But what it did was it got rid of the 1 over r squared in our Hamiltonian to make our Hamiltonian much neater looking in terms of the derivatives. And then we further defined 3 things. We defined kappa. We defined rho in terms of kappa and r. So r is linearly proportional to rho, or vice versa. And then we defined rho 0 so that the Schrodinger equation at this point could be written in a fairly simplistic looking form. Not solved anything, but made it so it's at least simple to write, and thus we can be pretty sure it's going to be simpler to do the math.
How did we get the initial radial solution?
Okay, so let me look at what you're pointing to rather than guessing as to what you mean by this.
Before we defined u of r, we had this.
Okay, this equation here?
Yeah.
That came from putting in the Laplacian for the momentum. Momentum squared. I mean, what we did earlier today, I said momentum squared is momentum x squared plus momentum y squared plus momentum z squared.
Right.
Well, if you're doing things in spherical coordinates, of course, it's going to be different than x, y, and z. And you can go back to the original definition that momentum is p squared over 2m. And for 3-dimensional momentum, instead of doing a single derivative, you have to do the Laplacian. Well, you do del. A single derivative is going to be a single. I call it del of it. And then since it's p squared, you're going to have del squared as the derivative operator. And then del squared in spherical coordinates has been worked out, and we substituted that in and got this big, ugly thing.
Okay.
And then when we separated, we have the radial parts of what you're seeing from that spherical version of the Laplacian.
Okay, so that's kind of been rearranged so that it's equal to that constant that we had before.
Right. The separation, going back up here to step 2.
Yeah.
This is what we got in step 2.
Okay. Okay.
And notice you have derivative of 1 over r and then another derivative.
Yeah.
And so the reason, or actually it's r squared in there, ddr and r squared. The reason to make the change to u is to make that simpler looking.
Okay.
And then the reason to make kappa and rho 0 is to write a whole lot less constants.
Yeah. Should we be able to write out?
No, you can just say, use constants to simplify the writing. I mean, you don't have to do that, right? You can write everything out longhand. It's just going to take you at least 50% longer for all the writing you're doing. I mean, that's assuming that the math is already known. You don't have to. Okay, then you solve the large radius solution. So for the large radius solution, you have terms that have no r, 1 over r, and 1 over r squared. If r is very large, the 1 over r, 1 over r squared are going to be zeros compared to the other one. So we just drop those out. It gave us a simple equation to solve. Apply your boundary condition that as r approaches infinity, it has to approach 0. You got rid of one of the two terms. Beautiful. Rho to the L, I think it is, right? Then you want to find the short wavelength solution. So you go back and say, okay, so short wavelength, the 1 over r squared is going to be the little n that dominates. And so you get rid of the 0 out the other two terms and just solve it with the 1 over r squared term. Are you guys following what I'm saying? I don't have the equation in front of me, so I'm just talking, and I probably should have written it up here. Actually,
Yeah.
so I can write it. The equation I'm looking for is, the equation we're solving here is d second u d rho squared equals 1 minus rho 0 over rho plus L times L plus 1 over rho squared u. And so now when I say small radius, that means small rho because they're linearly dependent on each other. And so for small radius, so for number 1 there, small radius, we just set these two equal to 0 because, or excuse me, large radius, we set those two equal to 0. And then for small radius, we set these equal to 0 because 1 over rho squared is going to be much bigger than 1 over rho, or 1, if rho is a very small number. And so we found the large and small radius solutions, and then we had to find the intermediate solution. So just as we did when we did the analytical approach with the quantum harmonic oscillator, we said, well, let's just take a power series to get our complete solution. So we set our complete solution for the radial equation is u of r is equal to, when you had rho sub L, that was our, or rho to the minus L, right? Was the rho to the minus L our?
E to the minus rho.
Oh, e to the minus rho.
Yeah.
Okay. E to the minus rho, and then what is the short? Rho to the L plus 1. Is it just that?
Yeah, there's just a normalization.
Okay. Yeah, won't worry about that until we're to the end. And then we're going to have V, where V is the power series. But we have to recognize the only way this can actually be the correct solution, to me, it almost seems a little bit wrong. We know we can make any function by an infinite polynomial. And then we say, but the only way it can be valid is if that polynomial terminates. Otherwise, if j really goes up to infinity, we are going to have our v function blows up faster than our e to the minus rho goes to 0 for large radii. And so it doesn't matter where it terminates, but it has to terminate. It can't have an infinite number of terms. And so then we said, okay, it must terminate. Just a rule. We plug this back into our Schrodinger equation that's in red. And after doing the derivatives, we rearranged so we collected in powers of rho. So we have rho to the, let's say, rho to the 1 times this stuff, plus rho to the 2 times this stuff. And of course, it wasn't rho to the 1 times this, it was summation of j equals 0 to whatever, rho to the j times this stuff. And for this to be equal, and the whole thing was equal to 0, the only way it could be equal to 0 is if for every power, the stuff in parentheses was 0. And in so doing, we were able to get a recursive relationship between the C sub j's. So once we know one C sub j, we can calculate the rest. And using the fact that it must terminate, we defined n as equal to the terminating j, the maximum j, plus L plus 1. And the reason we defined that was because the j plus L plus 1 appeared in our recursive relationship. Or not, yeah, it is. And so that's where the quantum number n appeared. So now we have all of our quantum numbers, well, 3 quantum numbers appearing. The L appeared in separating radial from angulars. And then the M appeared in separating azimuthal angle from altitude angle. And then the N appeared because of our requirement that this has to terminate. And, you know, especially for those of you too, who are very well versed in chemistry, you know the N really well. You know the L pretty well. You know the M. But where they come from, you know, at a chemistry level, it's magic. That's why you have to take this class. So you're like, I see. There was some fundamental reason they exist rather than, well, we just need some numbers. So now we're just about done. You solve for those polynomials by using the Laguerre polynomial and the associated Laguerre polynomial. That's how you get your radial equation. You've got to normalize it. Yay, fun. And then the final thing, we have how many quantum numbers so far? 3. We have, by observing the behavior of atoms, it was recognized that it's behaving as if there is an additional magnetic moment. And so they thought about it, and they said it made sense. If the electron was spinning, it would have a magnetic moment, and that's where we get the term spin. We now understand that's not so, but we have a magnetic moment that we treat as if it comes from an angular momentum that has all the same rules as angular momentum, except for it's intrinsic. It's not actually angular momentum. And so that's where the spin comes from. And for the electron to spin 1/2, and since the orientation has to be between, for what we did before, M had to be between minus L and plus L, we're going to have M for S between minus S and plus S. So between minus 1/2 and plus 1/2, those are the only 2 values possible.
So is it like there's actually 5 quantum numbers then with the S?
Yes, but that's just always 1/2. So,
okay. So
that's why it's never ever listed, because it's always the same.
Okay.
You know, it's kind of like we always have the time dependent portion. We never talk about it because it's always the same function.
Did we actually find the radial solution after doing that Laguerre polynomial associated?
We didn't go through the math of doing the Laguerre polynomial, just like we didn't go through the math of using the Rodriguez formula and the Legendre function stuff.
Okay.
I just pointed to them.
Okay, because I know we found, based on what n was, we went back and plugged in row 0 and found energy from that. But
Yes.
I don't remember us looking at the radial equation after it had been solved for.
I think I pointed to it, but that's all.
Okay.
And I know I did make you find, I had made you find like the force or the spherical harmonic for L equals 2 or something.
Yeah.
But that was just spherical harmonic, not, I don't think I had to do it for n equals something and find the R function.
I don't think so.
Okay, so that's the process. Obviously I don't want you to just memorize this. I want you to understand it so that it comes easier than, well, I memorized step 1, step 2, step 3. But if you can regurgitate this, that will be that one question.
And words is okay. We don't have to put down a bunch of.
Right, you don't have to put down equations.
Okay. Why in step 3 of number 7 do we? Yeah. Why do we plug it back into the Schrodinger equation?
We plug it back in so we can actually find those C sub j's.
Okay.
Right. Without doing that, we just say we have this function. So didn't I write? I might have wrote it down a little apparently. We can say we have this function where the C sub j's are unknown, but we know it must terminate. you put in the Schrodinger equation, that's where you actually find the values for the C sub j, and that's where the n is introduced. Other questions? Anybody remember when the final exam is?
Monday at 1.
Okay. And now I forgot about this. I've not talked to Dr. Osborne. Are we having a combined final between the two?
No, we're having our final on Friday, perhaps,
Okay.
like this Friday.
Okay. Because I was thinking, I planned a final as the entire period.
Yeah.
And if we're combining it, that doesn't work out now, does it? So you've got 2 hours to do this 2-hour exam and this 2-hour exam. A little.